Students, we have already studied that metals are crystalline in nature, right? Say for example, if you consider aluminium, this is crystalline in nature. This is because the constituent particles which are present in aluminium are orderly arranged. See, this is the arrangement of the constituent particles. See, this is the arrangement of constituent particles in one dimension. But students, let me tell you, the crystalline solids have three-dimensional structure. Crystalline solids have three-dimensional structure. See, this is the arrangement of constituent particles in one dimension. But how does it look if we consider the three dimension? Yes, it looks like this. See, this is the smallest portion of that entire crystal. In entire crystal, if you look at one particular portion, say that smallest portion, that looks like this. And this is called crystal lattice. That means the smallest portion of that entire crystal is called crystal lattice. Like this, there will be arrangement of particles. See, this is one crystal lattice. Like that, there will be many crystal lattices which make the entire crystal. For our understanding purpose, let me show this crystal lattice like this. See, this is crystal lattice, and this is the three-dimensional arrangement of the constituent particles. The three-dimensional arrangement of constituent particles in a crystal, in which each particle is depicted as a point, like this. The arrangement is called crystal lattice. The arrangement is called crystal lattice. See, there are only 14 possible three-dimensional lattices. That means only in 14 possible ways we can arrange the constituent particles. And those 14 possible three-dimensional arrangements are called Bravais lattices. So this is called Bravais lattices. And then what are those 14 possible three-dimensional arrangement? That we study later. See here, this is the crystal lattice, which is the smallest portion of the entire crystal, right? Here, this each point, like this each point is called lattice point or lattice site. These points are called lattice sites. And this each point represents the constituent particles like atoms, ions or molecules. Say for example, this is the crystal lattice of aluminium crystal. Then these points represents aluminium atoms. Say for example, this is the crystal lattice of iodine crystal, iodine solid. Then this point represents iodine molecule. Hope this is clear. These lattice points are joined by straight lines to bring about the geometry of the crystal. See, these lattice points or lattice sites, or say atoms, molecules or ions, they are present in space. That means they are present in three dimension. To bring about the geometry of that crystal, we have to join these particles with straight line. Then it brings a particular geometry to the crystal. That means a particular structure to the crystals. Students, if you carefully look at this crystal lattice, there is a repetitive arrangement of the structure. See, let me focus here. See here, the particles are joined by straight lines, right? See, the same kind of arrangement is repeating, right? Now it looks like a cube. This looks like a cube, right? The same kind of arrangement is repeating everywhere. Correct? Now it looks like a cube, right? Here the particles are present at this corners of the cube. Here the same particles, they are present at the corners of the cube, and the same structure is repeating, right? See here, the particles are present at the corners of this cube, isn't it? Now this is the smallest portion of this crystal lattice. Crystal lattice is the smallest portion of crystal, and this portion is the smallest part of this crystal lattice, and that smallest part is called unit cell. Yes, unit cell is the smallest portion of a crystal lattice. In this unit cell, the particles are present at the corner. Particles are present at the corner. Then you may ask, the particles always present only at the corners? Are they not present at other places than these corners? Yes, students, in some crystals, the particles may be present in addition to these corners at center of the unit cell. Here, like this, here particles may be present. In some crystal lattices, in some crystalline solids, the particles may be present at the faces of this unit cell. Like here, faces of the unit cell, in addition to the corners. In every crystal, the particles will be present at the corners, but in some crystals, in addition to the corners, particles may be present at the faces or body center. Now, if you look at this in a unit cell, it is characterized by 6 parameters. It is characterized by 6 parameters. The 3 edges like A, B, and C, and the angles between edges alpha, beta, and gamma. See here, this is one edge, say A, this is another edge, say B, and this is the third edge, say C. Now the angle between edges A and B is called gamma, and the angle between edges B and C is called alpha, and the angle between edges A and C is beta. Therefore, we can say now each unit cell is characterized by 6 parameters, and they are alpha, beta, gamma, and A, B, and C, where A, B, and C are the edges, and alpha, beta, gamma are the angles between the edges. These 6 parameters will not be same in all unit cells of all crystal lattices. In some crystals, they may be same. In some crystals, they may be different. And based on the the values of these edges and the angles, we further divide this unit cell into different structures that we study next. See, these unit cells are classified into 2 types. The one is primitive unit cell. The other one is centered unit cell. In primitive unit cell, the particles are present only at the corners of the unit cell. Particles are present only at the corners of the unit cell. Whereas in centered unit cells, particles are present in addition to the corners. Where are they present? Let us see now. See, if the particle is present inside the body of the unit cell, in addition to the corner, let me show like this. See here, the particle is present inside the body of the unit cell, in addition to the particles present at the corners. Then this unit cell is called body centered unit cell, or BCC. Suppose the particles are present at the faces of unit cell in addition to the corners. Let me show like this. See here, the particles are present at each face. A unit cell or a cube has got how many faces? 1, 2, 3, 4, 5, that is back end, and 6 front end. There are 6 faces, right? At every face, there will be the presence of particle. So, the particle, if the particles are present at each face in addition to the corner, then that unit cell is called face-centered unit cell or FCC. The third one is the particles may be present at only 2 faces in addition to the particles present at corners. Then such type of unit cells are called end-centered unit cell. I have already told you that unit cell is characterized by 6 parameters, right? Suppose in a unit cell, the edge lengths like A, B and C all are equal, and the axial angles alpha, beta, gamma, they are 90 degree, then that unit cell, the structure of that unit cell is called simple cubic. So, in any unit cell, if edge lengths A, B and C are equal and the axial angles alpha, beta, gamma equals to 90 degree, see here edge length A, B, C, they are all equal, and the angles between the edges are 90 degree, then the structure of that unit cell is called simple cubic. With the simple cubic, 3 different types of the unit cells are possible. Then examples for the crystalline solids which is made up of simple cubic are NaCl and copper. Students, just looking at all these informations, we cannot conclude, yes, NaCl has got the simple cubic structure or copper has got simple cubic structure. It is experimentally determined. That means we should remember this. Suppose in a unit cell, if edge length A equals to B, but C not equals to A or B, that means edge lengths are different. Edge lengths A and B are same, but C is different. And the axial angles alpha, beta, gamma. So the axial angles alpha, and this is beta, and this is gamma. They all have 90 degree. Then that unit cell is called tetragonal. In tetragonal, only 2 types of unit cells are possible. The one is primitive, the other one is body center. Example for this is calcium sulfate and tin oxide. Suppose in a unit cell, the edge lengths A is different from B and B is also different from C. They are not equal each other, and the angles between them are same, 90 degree, but edge lengths are different. Then the structure of that unit cell is called orthorhombic. So in orthorhombic, all the 4 types of unit cells are possible, that is primitive, body centered, face centered and end centered. The crystals which are made up of this orthorhombic unit cells will have 4 different types of unit cells. In one crystal it may be FCC, in another crystal it may be BCC, in another crystal it may be ECC. So this we can determine experimentally which crystal is made up of orthorhombic type of unit cell, but it has BCC or FCC or ECC. And examples for this are potassium nitrate and barium sulfate. Suppose in a unit cell, edge length A equals to B and they are not equals to C. C is different. Then axial angles alpha and beta, they are 90 degree. Alpha and beta are 90 degree, whereas this gamma is 120 degree. Then the structure of that unit cell is called hexagonal. In hexagonal, only primitive is possible. Then example for this hexagonal structure is cadmium sulfide and zinc oxide. Now a unit cell where edge length A not equals to B, and this not equals to C. That means all the three edges are different, whereas in their actual angles, alpha equals to 90 degree and this beta not equals to 90 degree. It is different. And this gamma is also 90 degree. And this beta, it is slightly more than 90 degree. Then the structure of such unit cells are called monoclinic. So in the monoclinic, two types of unit cells are possible. The one is primitive, the other one is end-centered. Example for this is sodium sulfate and monoclinic sulfur. See, in a unit cell, edge lengths A, B and C are different and the angles also different. Alpha not equals to beta and beta not equals to gamma. And the angles of these edges are also different. Then such type of unit cell is called triclinic. So this is the most violent structure. None of the edges are equal and none of the angles are also equal. Such system is called triclinic. So in a triclinic, only primitive is possible. Example for this is potassium dichromate and copper sulfate. See, let us summarize this. See, there are 7 different types of crystal systems: simple cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic and triclinic. With simple cubic, primitive is possible, body centered is possible and face centered is possible. And what about the edge lengths and axial angles? That we mentioned here. And the examples. See, if you count this, it comes out 14. That is what we mentioned earlier. There are only 14 possible three-dimensional arrangements. This is called Bravais lattices. See, only these are the 14 possible three-dimensional arrangements and they are called Bravais lattices.